carry on this example. As I said, we'll finish at 10. Just endure another hour, okay? I'll try to not be so monotonous, okay? So we are what we are going to do is based on a gradient distributed load. We are going to determine the deflection equation. Okay, we're going to determine the. So like before, we know that x is equal to 0, and then on the right hand side we have x is equal to L V M theta y V M theta y. Okay, so we know at point A the shear force is equal to 0. Okay, the moment is also equal to 0. When x is equal to 0, what is theta and what is y? We don't know. Okay. Now we focus when x is equal to L. We know that there's a shear force. Okay, so if we were to draw the free body diagram, we have a By and we have a moment at point B. So this is our x and that's our y. Okay. So theta now, as I mentioned before in the built-in, theta is equal to 0. And we know deflection is also equal to 0. Okay. So the next thing that we will want to do now is we want to get the dv over dx is equal to minus omega as a function of x. Okay. So before we know what is omega as a function of x, we have to determine what is omega as a function of x equal to. I'm next going to sketch the next graph. As this is x and this is omega, and we know that we have a gradient distributed load looking like this. And then we know at this point, this is equal to omega naught. Okay, so i.e., this is omega naught, and it spreads over a specific distance, and this is L. So therefore, omega as a function of x is equal to omega naught over L. Okay. And then multiply by x. The y-intercept is equal to 0, so that's your equation. Okay. So by using this, we are going to determine the shear force and shear force and bending moment equation using the integration method. Okay, using the integration. So we know that dv by dx is equal to minus omega as a function of x, right? So from here, we know that this will be equal, so from equation number 1, right? So can you put this as equation number 1? Okay, so from equation number 1, we know that this is minus omega naught over Lx. Okay. Then we integrate. Okay, we are going to integrate number 1. Before I put integrate number 1, let's name our boundary condition. So we have boundary condition number 1, boundary condition number 2, boundary condition number 3, boundary condition number 4. Okay. So we integrate, so I just label them. So we only can use your boundary condition once in any situation. So we won't get mixed up or we won't get lost or whatsoever. So we are going to integrate dv, and we're going to have this as minus omega naught over Lx dx. So we have v as a function of x. This will be equal to minus omega naught x squared over 2L plus by C1. Okay. And this is our equation number 2. So with equation number 2, we are going to use boundary condition number 1, where x is equal to 0, v is equal to 0 into equation number 2, right? So when that's the case, C1 is equal to 0. Okay. So we have v as a function of x is equal to minus omega naught x squared over 2L. My L looks like a 2. And this is equal to dm over dx. This is our equation 2a. Okay. Then we're going to integrate again. And now we have dm, and then we're going to integrate minus omega naught x squared over 2L dx. So we have m as a function of x. This will be equal to minus omega naught x cubed over 6L plus by C2. Okay, so that is, we just form our equation number 3. Then we are going to use our boundary condition number 2, where we have x is equal to 0, m is also equal to 0. We're going to substitute into equation number 3. So when that's the case, we have C2 is now equal to 0. Okay, so what we have is m as a function of x, and this will be equal to minus omega naught x cubed over 6L. Okay, so this is our equation 3a. Okay, so now we have our moment equation now. So the next thing that we're going to do, I think I have a lot of space. I'm going to carry on the same page. Okay. Then the next thing, I'm going to put equation, I'm going to copy the whole thing and put. So the next thing that we're going to do, okay, I think up to here, you all are very familiar with this from 2P. We are going to apply the elastic curve equation into equation 3a, which states EI d squared y over dx squared is equal to m as a function of x. Okay, so this is the elastic curve equation. So from here, EI d squared y over dx squared will be equal to minus omega naught x cubed over 6L. Okay, so this is now our equation 3b. Then after that, we are going to integrate the third time. Okay, so you have EI dy by dx, which is equal to EI theta, and this will be equal to, we're going to integrate, okay, we're going to integrate minus omega naught x cubed over 6L dx. So with this, when we integrate, you have minus omega naught x4 over 24L plus by C3. Okay. Now let's go back to our boundary condition, right? So we have used our boundary condition number 1. We also have used our boundary condition number 2. And now we are going to apply both our boundary condition number 3 and also boundary condition number 4. Okay, so now going back to this over here, so we are going to use boundary condition number 3, where x is equal to L, okay, theta is equal to 0, okay, right? So the equation that we have, this is equation, and we're going to substitute into equation number 4. So we have 0, and this is equal to minus omega naught x omega naught L cube over 24 plus by C3. So from here, our C3 will be equal to omega naught L cube, not 2 cube, okay, L cube over 24. So we put everything back in, so we have EI d squared y, dy over d theta. So this will be equal to minus omega naught x4 over 24L plus by omega naught L cube over 24. And this will be our equation 4a. And then we're going to integrate. That's why you guys study so much on integration in your math. For the fourth time, okay, so when we integrate the fourth time, you have EI y as a function of x. So this will be equal to minus omega naught x5 over 120L plus by omega naught L cube x over 24 plus by C4. This is your equation number 5. So we have one more boundary condition that we have not used yet. Okay, so we are going to use our boundary condition. Okay, we're going to use our boundary condition number 4 that states that when x is equal to L, right, we have y is equal to 0. We're going to substitute into, I believe, is into equation number 5. Okay, so we substitute into equation number 5. So you have EI, so you have 0 will be equal to minus omega, hold on, omega naught L4 over 120. Okay. And then you have plus omega naught L4 over 24